All right. Up until now, when we talk about continuity or something, a function being continuous, our definition is kind of what we have on the top there. It's kind of what we called it. It would be a function whose graph can be sketched without lifting the pencil. That's kind of a little bit misleading, but it is the easiest way to explain it to you before now. Now we're going to get much more formal about continuity of necessarily at a point or for a function. So when it says an interior point or an end point, so like here you see interior point and end point, we're basically saying that our graph, maybe it starts here and it goes along like that. Interior points are kind of all of these on the inside, right? And then the end points would be, obviously, these at the end. Clear? Okay. So now for interior versus endpoints, it's quite simple. It says for interior points, a function y equals f of x will be continuous at a point on the interior at some point c, so they just give it some point c, of its domain. That's going to be huge. And that's why we spent so much time dealing with domain and range earlier this year. Okay. If this is the kind of stuff that you really have to get better at reading. Because as you move on, or if you take other classes, this stuff won't be explained as well. So this is saying the limit as x approaches that c value that we talked about earlier, some interior point, of f of x is equal to f of c. What does that mean? What does that stand for? Well, this is saying as the value gets closer and closer, correct? It actually just equals f of c. What if I put c into the function? I would get some response, correct? I would get a, normally we would call it a y value, correct? Or a member of the range. So basically it's saying the limit is equal to that value you would actually get by just putting it into the function. So are we going to have those big holes where maybe there was a hole here and then the point was way up there? Yeah, we're not going to have that because that limit and that actual point where it's defined are not the same. Okay, this is saying they have to be the same for all value c. So basically all the way along here, every value of c, the limit has to basically equal the y value. If that happens, it will be continuous. That's at an interior point. At an endpoint, they're basically saying if the left endpoint is a, so we'll call that a, and the right endpoint is b. Notice how the limit as a, it approaches a from the positive, so it's approaching it from the right. It's just saying I'm going to approach it from the right equals the y value, or as I approach b from the left, it's just approaching the y value is really what it's saying. Okay? So some people could say, oh, there's no hole there or something along those lines. But once again, you notice it says of its domain. Okay? So there are going to be some functions that break that old definition of continuous. Okay? So let's just try a few and it'll become clear if it is not clear already. So here's our first example. Use the graph at the right to answer the following questions. Does f of 0 exist? Now notice I didn't give you the function, I just gave you the graph of the function, correct? So that really means if I were to substitute 0 in for an x into some function, does a y value result? Is there a y value? So does it exist? Yes, and how do you know? Yeah, there's a point there, right? Okay. So yes, it does. Okay. Well, what is it by chance? Well, it's 0, comma 1. It's right there, right? So yeah, it's 1. Does the limit as x, because this is an end point, right? It's on the far left side. So does the limit as x approaches 0 from the right exist? Does that limit exist? So if you pick something to the right and you work your way back in, does that limit exist? It does. Yes. And what is it? It's 1. So now it's asking, does f of 0 equal the limit as you come in from the right? Because this is the endpoint. Are they the same value? Yeah, what was your answer for this one? You told me it was 1. Does that equal your answer for this one, which you told me was 1? So are they the same? Yes. So based on our rule earlier, will we consider f of x continuous at the point x equals 0? Because is the limit, as I'm coming in from the right, equal the y value that's actually there? It does. So yes, at that point we will say yes, it is continuous right there. Okay. Questions on that? So now we know at that point we know we're good. Okay? What if they were two different values? Then we would say we are not good. It is not continuous. Yes. Okay, so let's use that graph again. How about f of 2? Does f of 2 exist? Yes, what is it? Yeah, it's 2, right? 2 comma 2 is right up there, right? So it is 2. So yes, and it's 2, right? Now this is an interior point, agreed? Right? So does the limit as x approaches 2 exist? Now remember, for limits, it has to come from both directions when it's in the middle, right? So choose something from the right. It's going to what value? It's going to 1. How about from the left? It's going to 1. So does it exist? Yes, because it's going to the same value both ways, right? And what is it? It is 1. Does f of 2 equal the limit as x approaches 2? No, because 2 does not equal 1. So seeing this as an interior point, we would ask, is f of x continuous at x equals 2? No. Now the important part, why am I asking that question, that exists question? Well, because if f of 2 did not exist, is it part of the domain? No, it's not. You have to make sure it's actually part of the domain. So in other words, what if that point was not there? This is the tricky part. If that point is not there, is 2 even part of its domain? So is it a point I should even check for continuity? No. Okay. So does that mean this could be continuous other places? Yes. And overall, could I consider this function continuous? Yes, because you're not supposed to check places that are not in the domain. Okay. How about this next one? Is f of x continuous at x equals 4? What do you think? Now, x equaling 4, should I be looking at the endpoint rules or the interior point rules? Endpoint rules, right? It's just over there. And what are the rules there? The limit as x approaches that's the right endpoint, so I should approach it from the left. Does the limit actually equal the y value that is right there? It does. And is it part of the domain? Because if it wasn't, I wouldn't even check, right? Well, yeah, I got a result, so it's part of the domain. What do you think? Is it continuous at x equals 4? Yes or no? Did the limit as it approached it from the left and the y value, do they equal the same thing? They do. They both equal what, 1? So yes, it is continuous. How about, is f of x continuous at x equals 1? Okay, now is it part of the domain? Yeah, because it is actually defined, right? It's right there. Agreed? So is the limit, well, what's the problem here? The limit doesn't even exist, does it? Right? Because as you approach it from the left and you approach it from the right, you are approaching 2 different values. So the limit doesn't even exist. So can it equal something else? No, the y value equals 1. And I don't think that no solution does not equal 1. Right? So that is no good. So is it continuous? That's a big old no. How are we doing on continuity so far? Okay? It's a very different definition of it, correct? There we go. Okay, if a function is not continuous, then it must have some kind of discontinuity, correct? Something that makes it not continuous. Are you agreed with that? One of them would be these are apparently holes, correct? So these are called, so kind of from something else that I can't talk about right now. Yes, they are removable. One of the reasons they're called removable is basically if I fill in that hole, it is continuous, right? I have removed the discontinuity by just filling in that point, right? So those are both A and B are both removable. Okay. And can you see that in both cases we would have a problem with that rule we came up with, correct? Graph C has, anyone who want to take a, because obviously we have problems with our limit here, right? So there's definitely a discontinuity there. Anybody want to take a shot at that one? What it's called? Any guesses? Jump. Because the graph kind of is going along just fine, and then, whoa, jumps up there. Okay. And graph D does have a type of discontinuity. You could sometimes maybe call it asymptotic, but we're going to go infinite. Okay. Yes, it is not removable, but then also, depending on what function we had, this particular asymptote we might be looking at is probably not part of the domain, correct? So it would be continuous everywhere on its domain. Okay, so we have to be careful with that. All right, graph, well, you can see it there. So graph E has a blank. Well, here we go, graph it on a calculator. You could do that if you wanted to, but I'm going to tell you it just says something like this. Okay? Basically, if you want, you can just start going in here like this, and then it just goes crazy. And then it goes out like that. Sure. You can go ahead and do that on your graph, because that's what it looks like. So in other words, it just kind of goes out of control here, correct? Oh, I think it kind of stays within there. Yeah, it just goes everywhere. This is called... Uh-oh. That's not good. Uh-oh. It's called oscillating. Like a fan. Very good. Oscillating. You don't see oscillating a lot, but it does. Okay. The problem with that is it's hard for me to find the limit as it's coming in there because it's going everywhere, right? Whoa, where's it going? I don't know. Right? Takes off. Okay. So let's go and determine all point or points of discontinuity for each graph. Hey, piecewise, everybody's favorite. Both of these graphs are what? They're lines, right? They are linear. So this one here, we graph it as x is less than or equal to 0, or in other words, when x is 0 or negative, correct? And it's 3x minus 2. So the y-intercept is negative 2, correct? And has a slope of 3. But I only do it when it's negative, so I'm hoping I actually hit it. There we go. Something like that. And you may notice that this point right here is filled in. Why is it filled in? Why would I fill in that 0, negative 2? It's because of that equal to on there, correct? How about this other one? It has a y-intercept of 3, just that graph, right? Would. And a slope of negative 1/2. But what do you note about this? Yeah, there better be an open hole there at 0, 3, because I'm not allowed to actually put 0 in because it says it has to be greater than 0. Okay. But again, the reason we don't just put in 1 is because then you would miss all of these values right there, right? You would miss all of those if you just started at 1 right away. So we start at 0. Okay. It is a jump discontinuity, very good. And then what we have to do is find all point or points of discontinuity. So how about an x value of negative 2? Is there a problem at an x value of negative 2? Because x value negative 2, you would go to the x value of negative 2 and you'd find your graph down there. Do I have a problem with that point? Or is it continuous there? Yes. Now, how about at a value of, say, I don't know, 2 or something? X value of 2, yes, I've got a point. Is it continuous there? Yes. So are there any that I have a problem with? Any x values that are of issue? Yes, x equaling 0 is a huge problem. Is it in the domain? Yes, it is, because I got a point there. I got 0, negative 2. I actually got a point. Okay, so we're fine. We don't have to do, there is a discontinuity there. Okay, are there any others, or is that it? Yeah, that's it. All the rest of them, I find that limit, and it will equal the y value that is there. Correct? It does have a rather interesting range, yeah, but a lot of them get repeated, right? Mm-hmm. So I've given you a rather bizarre looking graph. So where are places that this has discontinuities? X equals 0 is a problem? Why is x equals 0 a problem? It's an interior point, right? Yeah, the limit as x approaches 0 is not the same as f of 0, correct? because the limit here is actually what? 0, and it's actually defined at what? 5? 1, 2, 3, 4. Yeah, up there at 5, right? So those are not the same value. And so what kind of discontinuity would we label this particular one as? Nope, I don't think that's jump. It's removable. Yep. Remember, we kind of call it removable because if I were to fill it in, it would remove the discontinuity. Where with a jump, does that really work necessarily? No. Okay. Any other places that cause, and that is part of the domain. Any other ones that cause a problem? Yes. X equals 2, I agree. Yeah, there's your jump. Yep. Okay. And why is that again? Because that limit, as I'm coming in, really doesn't even exist, right? No limit there. Okay, and it is part of the domain, which is important. Depending on how you look at this, you would also possibly write all x not in the domain. Because let's face it, x equals 17. There's obviously a problem there, right? But it's not even in the domain, so I'm not hugely worried about that, but keep that in mind. One of the graphs I was kind of thinking about earlier when I was talking is it's interesting to see how people discuss this particular function. We know what that graph looked like, correct? We've worked with it a lot. Not sure what you just did, but that wasn't it. Somebody just went with lines all over the place. I don't know what that was. Okay. And the question comes is this function continuous? And if we are asked, is it continuous on its domain? So pick any domain value you want. Will it be continuous at that value? If it's in the domain. I think we would be, because what is the domain? It's negative infinity to infinity except x equals 0. So in other words, if I plug anything in but 0, will it be continuous? It will. So you have to be very careful. This is continuous on its domain. Okay? So watch out for that. Okay? Does it look continuous, or does it meet that old definition that we had? It does not, does it? Okay, so be very careful. Yeah, exactly. Unless you do it kind of like some of the TI-83s do that say, I'm confused. Oh, just connect them. You know. But yeah, we shouldn't graph it that way, right? A little bit.